And I'll just do a quick bit. Right, now I'm back out of that, Suzanne. Suzanne, I can see that you wrote me a little message in the chat box. I don't often see the chat box, especially if I'm doing a full screen presentation. So just shout at me, okay? Put your microphone on, say you can't see me, and I'll go to something else, okay? So hopefully you can see my whiteboard. Somebody will tell me, can you see my whiteboard?
Yep.
Oh, good. Right. Okay. So very quickly, for Lewis, because he's going to get this later. All right. So this is polarization. It's the last topic. Advanced higher in my quanta and waves section. And the introduction is about electromagnetic waves. And electromagnetic waves come to us as an electric component oscillating in the y direction and a magnetic component operating in the z direction. And Lewis, you will need to, because I apologize, you're not seeing the first part of this lesson, you'll need to go off and have a look at the physics flash repo site and look at the intro slide that's in quantum waves, that's in polarization, and have a look at the intro. And you'll get a moving version of all this going on. Okay, right, so we've got these two fields, electric field in the y direction sometimes, the magnetic field in the z direction, and the only thing that's important here is that they are at 90 degrees, they are perpendicular to each other. But we're promptly going to forget the magnetic field, and we're only going to look at the electric field, because it's the electric field that plays the major part in this topic, polarization. Right. Okay. So what is polarization? And you might have got some of those sketches down, or you might write yourself a note to say when you're revising to go back to the physics flash repo site. I'll call it virtual physics because that's how it's badged, something called virtual physics. So we'll go back to our title, polarization. Now, what is polarization? Is a question which you can write down. And what it means is and remember, when I say the wave, I mean the electric part, because we're not going to consider the magnetic part. Okay, so it means that the wave always oscillates in one plane only. Now, what does that look like if you are looking at it in the X and Y directions and you look head on at it? Well, if you look at, well, here's my electric field, that is oscillating in the Y direction only. So looking end on, I've got X coming out of the board, and you would see the wave just going up and down. This is a good way to visualize and record, and you can use this sort of visualization. You're entitled to draw that in the exam, just like you are with this. So it's oscillating in one plane only. So X is out of the page. And Y is obviously going to be up here, and Z would be over here, but that would be for the magnetic field. I'm not even going to draw it. Okay, so X is out of the page. So a wave that only comes to you oscillating like this is called a polarized wave. Now, what would a wave that is the opposite of that and it's unpolarized. What does unpolarized look like? Unpolarized light looks like this. You could have a wave doing that up and down, but you could have a wave, and this goes back to the virtual physics thing. You could have it like that. So I'm just going to draw 3. X is still out of the page, but you're getting light coming to you, oscillating, the electric bit oscillating that way, oscillating that way, oscillating that way. So this is polarized, what's called polarized, a polarized wave, where it is only being allowed to oscillate in that direction. And this is an unpolarized wave. And what you're looking at is the electric field only. And we're not showing the magnetic field because it's too complicated to have that. And the magnetic field doesn't play much part in what we're going to talk of about this polarization. Okay. Now, normal sunlight is unpolarized because what you'll have is you've got sunlight. What causes sunlight? Well, sunlight's caused by light from the sun. And what you've got is you've got waves coming at you oscillating in all directions because these electrons are presumably dropping down in all sorts of directions. And I've been trying to find this out, actually, and I don't know exactly in what direction an electron is dropping, but let's just assume, and I think this is an assumption, let's just assume that an electron is dropping from a higher energy level to a lower energy level, and it drops vertically. And when it drops vertically, we'll assume that the light just comes to us and it's oscillating that way. But of course, an electron could drop in a different direction. It could be in an energy level over here, and it could drop that way down to here, in which case the oscillation would be in that direction. I don't know if that's actually true or not, but I'm just assuming that it is. So if you can imagine that all of the electrons dropping down an energy level in sunlight only dropped vertically. Now, vertically, what does vertically really mean? It means for us, let's just assume that it's for us. Vertically is up and down. Down is the ground, up is into the sky. And so the electrons are just dropping always down that way. Now, that's not going to happen in real life. And it certainly wouldn't look like that to somebody on the equator, because somebody on the equator would see it going from side to side. Somebody in Australia would still see it going up and down, but up and down in a upside down way, if you like. So it's possible to get to see this polarized light, but we have got to cause it somehow, or nature has got to cause the light somehow to get polarized so that you only see the oscillations going in one direction. Now, there are 2 ways in which we actively can view polarized light, and we are going to look at both of these ways of producing this. And why might you in fact want to do that? And I suppose the best example of why you want to produce polarized light is if you've only got light oscillating in one direction and you've got rid of the light doing this, you've got rid of a whole load of light. And that's how a lot of sunglasses work. Sunglasses, posh sunglasses, work by cutting down the light that you see by using what's called polarizing filter, and it gets rid of a lot of this light that's oscillating in one direction, in lots of directions, and it just leaves you with light oscillating in that direction, in which case everything's going to be seen a little bit darker. That's the posh way of polarizing light in terms of sunglasses. There are cheaper sunglasses where this polarization does not occur, and the cheaper sunglasses are made with just a dark filter, a dark colored piece of plastic, which just reduces the overall irradiance of the light, intensity if you like, reduces the intensity by physically blocking it, by making it more difficult for the light to get through, whereas more expensive sunglasses actually do this thing called polarization. Okay, anybody want to ask any questions so far? Everybody's quiet. That's a good thing. Okay, so polarized light is light oscillating in one direction only. So how can we get rid of all the other oscillating directions just to leave, we'll call it the vertical direction? Okay, how can we obtain polarized light? Now, there's two ways. You can use a polarizing filter, which looks exactly like a colored piece of plastic, but it's quite clever in the way that the polarizing filters are made. And I think the first ever polarizing filter was invented back in the 1930s by a man called, I think his name was Edward Land, and he worked for a company called Polaroid. I don't know whether the word Polaroid came first and then polarizing came afterwards. I don't really know when the words appeared, but polarizing filters have been around for about 100 years, and they are filters that remove the electric component. And we're not going to do anything about colored pieces of plastic the cheap way. So we're going to get rid of that because they don't do polarizing. Polarizing is where you remove all of these other different oscillating planes of light that's coming at you and only let light through in one direction. Good way to remember. Okay, polarized light, unpolarized light, as I've mentioned before. The second way in which we can do it, which is a way in which nature does it, if you like, is by polarizing by reflection. And some surfaces that reflect also do this polarizing thing. And for us as outdoor people, we're mainly interested in things that do polarizing by reflection. Things like if you're down on the beach and you get a lot of glare off the beach, or you get a lot of glare off the water, or if you're skiing and you get a lot of glare off snow, and you don't want to see all this glare because you can end up if you do a lot of skiing all day long and you're not wearing any sunglasses, you can end up with something called snow blindness, and you go temporarily blind and you can't see anything. It's very, very painful. So some surfaces do a lot of reflecting and they do polarizing at the same time. So things like glass, anything that is a electrical conductor will have no effect on light reflecting off it. So bits of metal, if light shines off it, do not do polarizing. Polarizing is done by electrical insulators like snow. Snow is not a very good conductor. Sand is not a very good conductor. Water is not a very good conductor. And before somebody tells me, oh yes, seawater does, because it's got water with salt in it, so it does do some conducting. It's whether it mainly is, or whether you can make it slightly conducting by putting salt in it. So don't go confusing me with chemistry. All right, so we're going to look at polarizing filters as invented by Mr. Land back in the 1930s, and then afterwards we're going to look at polarization by reflection. Okay, so what did Mr. Land do? He made some plastic, quite in the early days of plastic, I think. So we're looking at filters first. I'll go back, put new heading. And what he did was he made some plastics, and these plastics contain long chain organic molecules. And rather than having a plastic, which is just like a mishmash of all sorts of long chain molecules lying in all sorts of different directions, he had a way, which I think was mainly to do with heating. I think it was mainly a heating process. And he changed the orientation of all these randomly orientated long chain molecules in a piece of plastic. He changed them by some clever process so that all of the long chain molecules lined up in one direction. They all had the same, what's called orientation. And he found that when light was shone through this piece of plastic that has the long chain molecules all vertically aligned, he found that the long chain molecules absorbed the electric field component. Magnetic field component has disappeared as well. We're not going to talk about that. But if the electric field component is somehow absorbed, then the magnetic field component disappears with it as well, and you don't get light coming out the other side. Now, if I can draw a sort of diagram in 3D, okay, so I've got my Edward Land polarizing filter, which contains these long chain molecules like this, okay, and I've got an electric field. This is going vertically, so if you were looking at it from the end, you would see it like that, okay. This is a sort of 3D view. I've got an electric field. Now, I know I'm doing this in green, but I've started in green. I've got an electric field which is also oscillating vertically. So if I look at this end on, I'm seeing long chain molecules like that. And if I look at this end on, I'm only seeing my wave going up and down like that. So that means that this particular light, which is not oscillating in all these directions, this is already polarized. Polarized means only oscillating in one direction. Just got one wave and it's going up and down, it's going up and down, it's behaving itself quite nicely, going up and down, and it gets to these vertical long chain molecules, and the energy carried by the wave, which is going up and down, is absorbed, because the energy is going up and down as it reaches these rods. The energy is absorbed by the long chain molecules, providing the wave and the long chains are both in the same direction. They're orientated in the same direction. So this light wave is oscillating up and down, and these long chains are up and down, and the up and down long chain molecules absorb the oscillating field in that direction. So what comes out the other side, here's your light approaching the filter. So this is already polarized, and it's polarized vertically, and these are vertical long chain molecules. In a what's called a polarizing filter. Because the wave is oscillating vertically and the vertical long chain molecules are in the same plane, they're both vertical, what comes out the other side? No electric field. And with it, no magnetic field. So if there's no electric field oscillation coming out there, what will you see? You'll see absolutely nothing. And so you can have a bright light that's polarized vertically here, and on this side, you'll see no light at all. So it completely, 100% stops the electric field, because these long chain molecules soak up the oscillating energy, which is going up and down. Now, just off on an aside, and you can see this if you go out into the street, people who have old style television aerials on their roofs, the television company sends out its TV signal and it's polarized. It's either polarized vertically or it's polarized horizontally. And this is so they can transmit the same signals in the same area without them interfering with each other. Okay, so if we've got a vertical wave that's going up and down, see, not end on, it's only going up and down, and it comes up to a television aerial, and the television aerial will be set up like this. It's got metal rods, and what you have to do is, if you know your radio or TV signal is coming to you and it's only going up and down, then you put your TV aerial so that the vertical, what are called elements, go up and down. So when this wave hits the end here, what does it do? This wave is oscillating up and down. It actually, the metal elements here absorb this energy and they make electrons inside the metal oscillate up and down. And how the electrons oscillate up and down is exactly the same as the TV picture. So if the TV picture is oscillating up and down in a nice regular manner like that, so many waves per second, then the electrons start oscillating up and down. Oscillating electrons constitute an electric current, and that electric current is sent away down to your TV through a cable, and your TV detects the oscillating electrons going up and down and then returns it back in to a picture that was originally filmed back in the studio or whatever. Now I'm going to do this in a different car. I'll do this in blue this time. This is all the electric wave component, no magnetic components whatsoever. If the electric field is oscillating side to side like that, and if you were to see that end on, you would see it just going like that. If that is where you live and the television picture comes to you and it's what's called horizontally polarized, you'd have to have your TV aerial set up so the elements go across that way. And then the wave that's coming in, that's going from side to side, excites the electrons going in side to side, and the signal goes off down the cable. The clever thing is if you have got the other type of aerial, or you set up your aerial and you put the elements vertically, this side to side electric field does not get absorbed by the television aerial at all, and it just escapes by. It just goes through and goes off somewhere else. So you can have two different TV signals. One could be horizontal, one could be vertical, and the vertical one here won't be picked up by this aerial, but would be picked up by that one. So this is how aerials work. It's all about electrons being excited. Remember, back at this end, the electrons are being made to change levels in the first place, which sends out the wave, which then makes the electrons move up and down. And that's quite a clever thing, how TV and radio signals are sent and how they're picked up. Okay, so that was just TV aerials. If we have got a polarizing filter and all the long chain molecules go across like that, this horizontal wave, looking end on, going from side to side, gets absorbed here and nothing comes out the other way. So you'll see no light here. Now, if we leave the polarizing filter that way and we send our wave this way, which is vertically polarized, then the wave can get through. It can get through because it's completely at 90 degrees to the energy absorbing molecules, and the wave can get through like that. And so here you would see light. Okay. So this is what polarizing filters do. Now, instead of drawing all these lines, what we normally do is draw the polarizing filter so it looks like this. So I've got the polarizing filter, and to save yourself a bit of time, you just put an arrow on to say, look, that's the direction of the molecules, and that will absorb the light. Whereas here, the direction is the same for the molecules, but the light is completely non-absorbed here. So you've got to think about the electric component. What's the electric component doing in relation to which way the molecules in the filter are aligned? Okay, right. Now that's about all I want to do at the moment. That was just a brief introduction to polarization and polarizing filters. We've got more to do on this. Of course, not all light comes polarized already. Light from the sun comes as a mixture. It's oscillating from side to side, up and down. It's a mixture of that, it's a mixture of that. It's got all sorts of different planes. What happens when you put a filter here? What goes on? What comes out the other side? What do we see? And that would form another lesson. Now, when is the next lesson? Do not ask me when the next lesson is. I have no idea. I don't know what's going on. None of us know what's going on at the moment. Some of you, all of you, I don't know, will be back in school next Monday. I will be back in school next Monday. I don't know who's going to be in. I don't know who's not going to be in. I don't know if you are all in because you're 6th years and it's important, because 6th years make up a small class. Because you've all got to be socially distanced now. There's nobody's allowed to sit next to anybody else in class. You've all got to be 2 meters apart in class. I've got to be 2 meters away from you. How that works, I've got no idea. What happens if half of you are in school and the other half of you are at home? I've got no idea. I don't really know. You'll just have to wait until something comes out this week. But school will be open. Some of you will be invited back on some days. Others of you will be invited in on other days. Whether that means I have to do 2 sixth form lessons or I do one and record one, not a clue. Not a clue. Don't ask me. Nobody has got a Scooby. The Scottish government said everybody to go back to school. Social distancing, 2 meters. Masks will be worn at all times. Now, how do you do that, schools? We don't know, but you can get on with it. And the school hasn't yet worked out its plan. It's extremely complicated how you take back a number of people and how you prioritize 4th, 5th and 6th years, because you've got exams, and how 1st, 2nd and 3rd years fit into that as well, because they apparently are entitled to come back as well, but we don't know what's happening. So don't ask me. But I'm assuming, well, this will be the last lesson I do from home for now. I'm assuming I will see some of you back next week. And that's about all I've got to say. And you'll have to stand by. There will be communications coming out via emails, no doubt, sometime this week that tell you which day or days you are to come in. So I'll see some of you at some time. Right. Anybody want to ask anything about anything? Nope. Nobody wants to ask me about anything. Okay. I will leave it at that then. I will turn off the recording.